I'm going to have a brief foray into the mathematical formulation here. Importance of this is just that this is the permeability. Note that it's really a mobility coefficient. It turns out that permeability is a thing that means like 3 or 4 different things depending on what industry you're in. So we've actually, in the new version, we've actually discouraged even using the word because it causes confusion. Some people think it means one thing and some people think it means another, or their densities included or whatever. It's really what we use is more properly called the mobility coefficient, right? It just, this K in this equation. What other people call permeability divided by the unit weight of water. And all this is saying is that the flow into a node is proportional to the gradient of pressure. The bigger the pressure difference, the more flow. Plus gravity. This is just a trick to induce the gravitational gradient into that equation. Pressure increases with depth, and water flows from high pressure to low pressure. That's all it is. So this funny symbol, I don't remember the name of, ADA. Anyway, that represents the fluid content. So if you think of a pore as you've got your zone mesh, and you can think of a node, a grid point in that mesh. That grid point is responsible for a certain volume, total volume plus pore volume, right? The total volume is the volume of the contributions from all the zones connected to it. The pore volume includes the porosity. It's less than that because some of that material is filled up with solid. The porosity is how much of it is empty. Okay. So this is the fluid content of that pore. So it's basically the net of the flow in and out, and then whatever sources might be there. Again, it's not complicated. The fluid content changes according to the balance of inflow and outflow and whatever is being added to the system. So fluid is conserved. And once you've got a volume of fluid in the node, how much pressure it creates is, again, pretty much a linear function. This is the fluid bulk. This is the fluid bulk modulus. This is the porosity. These two things is also called the BO modulus. This is called the BO coefficient, which by default is 1, and that just relates. This is volumetric changes coming from the mechanical logic, right? So if things compress, you'll also generate pressure in the zone, assuming it's fully saturated. So all that's saying is as you add more fluid, the pressure increases according to the fluid modulus, and as you squeeze the zone, the pressure increases according to the fluid modulus. Fundamentally, it's pretty simple. Again, pressure increases with more water, and pressure decreases with expansion. If you're unsaturated, S here represents the saturation. It's always a value between 0 and 1. If you're at 1, you're fully saturated and you're generating pore pressure. If you're between 0 and 1, the pore pressure is 0, or more properly, whatever you set as the fluid tension, because you can set it to whatever you want. You can set the fluid tension to -1 e to the 3, and then things want to saturate. The pore pressure becomes that negative. Most of the time, you're at 0. In this case, the fluid content is just the amount of fluid available in that pore, which is the total amount of volume represented by that pore system, right? 0, there's no water. 1, it's completely full, but there's no pressure yet. And all this is saying is that saturation drops as the fluid water content drops, and again, as you squeeze it through this BO coefficient, which again by default is 1. So you can increase the saturation of the zone through volumetric changes, mechanical volumetric changes. So again, change in water content and pore volume affects the saturation, not the pressure, at least until it fills up, and then pressure will start to build. But this is a nonlinear system of essentially two coupled equations, one in the pressure and one in the saturation. And that means that in the current version of the code, you can't use an implicit solver if there's any saturation happening. You can only use an implicit solver if everything's fully saturated, so everything stays linear. That is not true of the new version. You can use an implicit solution even in the nonlinear range, but the current version doesn't have that. Okay. So for those of you who do soils, this is a sort of a classic, what I call a saturation suction curve of how negative pore pressure affects the as a function of saturation, right? So as the saturation in this case is going from 100 to 0 instead of 1 to 0, as the saturation drops, you actually get suction in the material for like clays or thick soils, and how much depends on the quality of that soil. Like a sandy soil doesn't generate much suction, and a clay might generate a lot. Okay. Now, the new version of FLAC2D can support all of these curves. The classic curve, you can make a table for it. There's some Brooks, Corey, Van Gnuchten, all those standard ones. The current version of FLAC2D doesn't support any of that. It just has what I call the cutoff model, which, by the way, I don't know if there's an industry standard for this. So if somebody knows, tell me, because I couldn't find it. So I just called it the cutoff model, which is the saturation stays at 1 and then it drops down instantly. So it just fills the pore. There's no suction generated. This is the permeability function. So as a zone, FLAC2D pressures and saturations are kept track of at the grid points. The zones are something presumably covered yesterday. So what happens is you generate a sort of average saturation for the zone by looking at all connected grid points. And then you adjust the mobility coefficient, or permeability, or whatever you want to call it, of the zone if it's not fully saturated on average by this function. This is a simple cubic law. The idea is that if this isn't fully saturated, then there's less transport across it, because part of it doesn't have fluid in there to transport anything, right? And it varies. This means is that the permeability of a fully desaturated material is 0, right? So it's not going to happen there. For the solid response, this is a lot of funky math, but really all it means is that we're taking the pore pressure off of the stress before we give it to the considered model. That's the only thing. That's the only takeaway. It's a straight up mechanical response we normally use, but this, and this is again the Biot coefficient, is used to adjust the stress before it gets to the considered model. H in this case represents the considered model. This is just the theory of effective stress.